Well, what this equation implies is that, there is different means for men and women, right? Because, female is coded as 1 and male is coded as 0. So if we plug in 1 for female here, okay, we will get, the mu for females to be 0.779 and the mu for male, in this case, for this variable female is coded as 0, right? It turns out to be 0.887. And then again, we're going to plug in this formula we just talked about for calculating the probability function, right? For different counts here. So for female, we have these probabilities, and for male, we have, another column of probabilities, right? Why we have such difference is simply because we have different mu for male and for female here. Okay. And now let's look at example for a continuous variable. A continuous variable. So in this case, I introduce just a single continuous variable as a predictor of this mu, right? Here, assuming mu is going to vary across individual cases, and how the mu is determined. Again, review, right? What I just talked about is determined by what? In this case, actually determined by that single, continuous independent variable. If individuals have the same values for that single continuous independent variable, then they're going to share the same mu here, that is expected count in the population. Okay, and since y again is a Poisson variable, Poisson random variable, then here is how to calculate its probability. Right. The only thing that differs, from the formula that we talked about is, well, the mu varies, right? The mu varies with individual. And in rare cases, they're going to be same across individuals, right? When the individuals have the exactly same set of values for the full set of, independent variables. And in this case, we have a very special case. We'll have one single independent variable. But let's go back to this single continuous independent variable case, right? So at x equal to 0, then we have mu equal to what? 0.78. Plugging this formula, we can get different probabilities. You see that? That's how, the probabilities are calculated. Given the mu slash, given this single continuous independent variable, right? Okay, and so here is a graphical presentation of how, the probability is going to be different across different levels of axis. So here, for a single continuous variable, right, that runs from 0 to 25. Here, we don't have a kind of conditional Poisson probability distribution for x equal to 25, but we do have for 0, 5, 10, 15, and 20. Once we plug in the equation in our previous slide, right? Once once the x is determined, for example, 0 here, and then we can figure out its mu, right? I, and then we can plug in the probability function, So what if y equal to 0, y equal to 5, and y equal to 10? We can calculate their probability, and that's how the conditional Poisson distribution looks like for x equal to 0. This is what it looks like for x equal to 5, right? And they should have a different mu I here, that is the expected count in the population. and on and on, right? And here we can see that as the value of values of x increase, we can see, the conditional Poisson distribution approximates closer to the normal distribution, right? In this panel, right? And in this panel is basically a magnified presentation of the region from 15 to 20, right? From 15 to 20 here, 15, 16, 17, 18, 19, right? And here again, we can see that as x increases, mu also increases. And, as mu increases, the probability distribution looks more like a normal distribution. Okay. And so how to estimate Poisson regression model? Well, to estimate this model, we have to rely on maximal likelihood estimation. So how to execute a maximal likelihood estimation? Well, we're going to construct the likelihood function. Okay. Usually, we would assume that all observations are independently and identically distributed. And if that assumption holds, then the likelihood of observing the data here, that is denoted by L here, right? Given the data and the beta, basically parameters that are to be estimated, can be expressed as a product of this individual probabilities. And for each individual probability, basically the probability of observed counts, right? Given, their counts going to be, each individual going to be, this term, then we multiply across all n cases. So this is basically the likelihood function of observing the data, right? And what is mu I? If you remember, well, mu I from last slide is equal to the expectation of what? Well, we observe y and x, right? Which is equal to the exponential function of x beta. And here I express it in matrix form. All right, what we're going to do? Well, multiplication here, product is a mathematical function that's very hard to be tamed. Okay, it's mathematically intractable for estimation. So what we're going to do, we take a log, and then we maximize that log function. Okay, with respect to beta, and we already talked about, bit of technical details of maximum likelihood estimation, and you can watch my lecture video on that topic. Here, I'm not going to get into a lot of details, but basically, we're going to take a log of this likelihood function. Then we're going to apply maximum likelihood estimation numerically. Once we figure out the maximal likelihood estimates of beta here, okay, for the log likelihood function, we're going to use them as the maximal likelihood estimates for the likelihood function. Why? Because the log function, okay, is a monotonic increasing function. Maximizing a log likelihood function is equivalent of maximizing what? Likelihood function.